Well, hi, everybody, and thank you very much for joining us. I hope everybody is doing fine and following all the guidelines to stay safe and healthy during these difficult days. Okay? Uh, Before we start with the talk, I'd like to mention that the core of this presentation is based on my research in the University of Alabama several years ago. The director of this project was Dr. Mancini. Many of you might know not only as a very prolific author, but also as an active member of the AAPG and editor of the bulletin some time ago. The objectives of this talk is to present the geologic model based on the integration of core, well core and logs with 3D seismic data in order to generate a geologic model that will help us to understand the depositional history of the Smackover Formation. The second objective was to illustrate and explain the development of microbial buildups, in this case thrombolites, in this deposition. Here's the outline of the talk. So we will start with an introduction that talks about the study area and the data available for this study. Then we will start working or talking about the depositional phases that identify the different depositional sub-environments. Then we will move into the diagenesis, also very important when we talk about carbonates. Then the identification of these environments in well logs, so we can extend the interpretation to the non-core sections. Then we will just take a look at well log correlations and seismic interpretations in order to build a 3D geologic model that will be the base for the description of the depositional evolution, the Smackover. And then we will go to take a look at the outcrop analogs of these microbial buildups in Europe and finish with some conclusions. The study area is located in the southwestern part of Alabama, where several small oil and gas fields are located, producing from the Smackover. In the Upper Jurassic, in this part of the Gulf of Mexico, the active limit of the Smackover consisted of several sub-basins of embayments were very shallow and restricted, rimmed by these basement paleo highs and uplifted blocks in ridges that were produced as the result of the extensional tectonics associated with the opening of the Gulf of Mexico. The restricted ocean circulation in these subbasins, together with arid climate and high evaporation rates, led to a particular type of setting characterized by higher salinities, low oxygen concentrations, and low heterogeneous input. Here I'm showing the location of just a few fields that are part of the study area. And this graph shows the stratigraphy, the Jurassic stratigraphy. And basically what we have is a crystalline Paleozoic basement that makes a very irregular topography. Below we have the deposition of siliciclastic, continental siliciclastic from the North Flat Formation, And this unit is overlain by shallow marine deposits of the Smackover Formation that unlap and sometimes are able to cover completely the basement paleohytes. On top of this, we have the subaqueous evaporites of the Buckner anhydrite member of the Haynesville Formation. Here, the source in reservoir rock is the Smackover Formation in different phases. The seal rock, vertical seal rock, is the Buckner anhydrite member, and the lateral seal consists of fine facies of the Smackover Formation. According to Sassen, the generation migration episode took place sometime between the late Cretaceous and the early Cenozoic times. The trap is stratigraphic associated with changes in or lateral changes in phases associated to the basement paleohytes. About the data, we have pretty much two areas: the vocation field area, in which we have 1,100 feet of core split in 11 wells with about more than 200 thin sections. We have 23 wells with basic log set and a seismic cubic program of 9 square miles. The Appleton field area, which encompasses like 3 small fields, has about 925 feet of core in 19 wells with basic log set, and a much bigger seismic cube of 52.5 square miles. We're going to start now with the description of the depositional phases. We're going to start with the phases that we see in the lower part of the Smackover, and we will keep in order as we move up in the section. So the first depositional phases that is interpreted as a shallow subwave base level consists of these dark brown skeletal dolomudstones and dolopaxstones with some plane parallel to wavy lamination that we see here in the core photo, and some small patches of microbial influence. And that it just has various types of allochems, but in very small amounts. We can see also stylites, regionogenic pyrite, and as you can see, porosity of these particular phases is very low. Then we move into what we define as the upper to middle shore phase. This phase was found only on the western side of the vocation structure. It is formed basically by a crystalline dolostone. As you can see in the thin section, you just can barely see the ghosts of the initial rock, probably a greenstone, but you can see basically the rumps of dolomite. It's what you see pretty much on thin section, nothing else. So there's an intense dolomitization of these. As in general, the whole Smackover, as you will see, is completely dolomitized. Porosity is also good in these particular phases, between 10 and 12%, and as you can see, is mostly intercrystalline porosity. Then we have these strange-looking rocks that define our microbial buildups. They are very heterogeneous, consist of dolomitic bafflestones, bimestones, intervals of oncoidal crusts, and other types of rocks. It has a great variability in allochems, and the porosity is the highest of all the phases, with 12 and 24%, and is of various types, including shelter, inter and intraparticular, moldic, buggy, like the pictures you see, the ones you see here in the pictures, and also fractures. what are these microbial deposits? Microbial reefs are formed mainly by cyanobacteria, as you can see here in this picture, in association with other microorganisms, including microalgae, fungi, and other microbes, including also forams. What these organisms do is that they stabilize and lose sediment to generate these buildups by secreting most likely calcium carbonate. Today we can see examples, living examples of these microbial buildups in many places on the earth. And like this one here, which is these famous stromatolites in Shark Bay on the western coast of Australia, where they live pretty much in an intertidal environment. And this other example, down deep in the ocean, in the Black Sea, about 700 meters deep, where these microbial buildups grow next to methane seeps. What these two distant environments have in common is that they share extreme environmental conditions which are hostile but for most living organisms, except for these microbial buildups or these microbial colonies. And in 1995, Braga came up with this internal classification of microbial textures. So he divided them into thrombolites. Thrombolite was a term coined by Aitken in 1967 to describe microbial structures characterized by a mesoscopic clotted internal fabric. Here's an example, the neogen in Chile. You can see these forms like balls or pillows that make the external shape of the buildup, which seems to be also characteristic of this type of texture. You will see in another example later. Here we have then the stromatolites with the typical laminated structures, and leiolites, which is a term used to describe just dense, homogeneous, boring microbial buildups with no distinctive geometry. Now, between thrombolites and non-thrombolites, we can differentiate also different textures. This is a classification made by Schmidt in 1996 and then modified by Parcel. In these ones, we have what were defined as chaotic growth structures, like the one you see over here, with no preferential growth direction. The layer, which has a pretty much a horizontal preferential growth, and dendroidal with a vertical, evident vertical preferential growth. All of these examples come from the study area, more exactly from the Appleto. Now we have living examples of thrombolites today. And this is in Lake Clifton, also on the western coast of Australia. Here we have these really extensive deposit of microbial buildups. What is more interesting here is the publicity that has been done oriented to become this very important touristic attraction for the country. So here you can see one walking with thrombolites, and this one is more interesting, and it's about the legend of the bunjip, which is a monster that lived in swamps and coastal areas in Australia. So the story tells that this is a nesting ground, a fossilized nesting ground of ancient bunjips. But this is just to attract this type. Continue with the facies in sub-environment. The next one we have was deposited on top of the previous one is the shoal complex. This consists of carbonate sandbars of dolophragmites and dolopaxtons. The allocants are mainly ooids and umbroids, sometimes phyloids, you see here in the picture. And it has some anhydrite nodules. You start to see the influence of the evaporites here. Porosity is pretty good, between 9 and 15% for this of facies, mostly intraparticle, moldic, buggy, and fractures again. Then we have the littoral lagoon, which develops behind the reef or the shoal barriers. Consist of finer sediment, waxstones, and mudstones. The allochems are rather uncommon, mostly pelloids and of intraclasts. It has some microbial laminations, and the most distinctive sedimentary structure is so in parallel to wavy lamination. Perturbation is also kind of common. You can see here some examples, and porosity is very, very low, below 55%. Then we get into what is interpreted as the tidal flat in SAP environment. Is the uppermost Smackover Facies. It consists of laminated fine sediments. With these anhydrite nodules, they become more and more frequent in the section. Porosity is also very low, sometimes high due to the presence of microbial mats, and the porosity is of different origins, finesse, moldic, intercrystalline, and fractures. And finally, this is now getting into the Buckner anhydrite member, where you see is these solid layers of anhydrite, no porosity, just with little seams of muddy material. Obviously, it's a perfect seal, as you can see here in the thin section. Now getting to the Diagenesis, I made this slide about Diagenesis and try to synthesize everything here because, as you know, in carbonates, the Diagenesis processes, diagenetic processes are very important. Is they begin to act short after deposition, and they keep active even at the great burial depths. And the Smackover is not the exception. This graph summarizes the complex diagenetic history of the Smackover in this area. You can see how it evolves through time and depth of burial. And in here in blue, I highlighted the processes that affect porosity, that preclude porosity, and in red also diagenetic processes that favor or enhance or at least protect porosity from destruction. And among the processes that favor porosity, then we have dissolution of aragonite. This is a very early process, the history in the diagenetic history. Here you have an example of the dissolution of the woods or pelloids that were in the original fabric of the rock. Then we have dolomitization, as I mentioned before. The entire section is intensely dolomitized, and this generates new intercrystalline porosity and also improves substantially the permeability among the different porosity types, including pores that are normally not connected, like body porosity. And we have fracturing associated mostly to the tectonics and the subsidence of the graphic section. We have also non-selective dissolution, probably related to active hydrothermal fluids in the pore space or organic acids related to early hydrocarbon maturation stages. And we have processes that preserve porosity, we can say, that are these early calcite cementation, more making these rims outside that protect the rock from mechanical compaction, or preserves the intergranular porosity region, intergranular porosity. Then we have processes that really affect the quality of the rock, like mechanical compaction is seen here in this same section by the alignment of the particles in these convex grain contacts, like you can see here. Then we have chemical compaction, the continuous burial, and the chemical compaction becomes very active and is expressed by these high amplitude microbial-Bearing, which are very common throughout the section. And then we have several late stage cementation events, including siliceous, carbonate, and these anhydrite white. They can be easily recognized because they fill all kinds of pores, and they have these large NUhedral, sometimes polytopic crystals. Now, despite this long and complex history of diagenetic processes, we are seeing that the reservoir quality rocks are controlled more by the initial depositional fabric than by the effect of diagenesis. And we can say that because here we have the sub-environments interpreted for this pore section. And as you can see, the porosities and permeabilities pick up when you get into the shoal complex. And in the shallow lagoons, the porosities and the permeabilities are very, very low. Same in an example where we poured a big section of the microbial reefs. Even though it's kind of heterogeneous, the high porosity and permeability numbers coming from the core are in the microbial buildup, and you see the lowering as you get into the tidal flat or the shallow lagoon. Also, the strong correlation that exists between the good porosity values and the good permeability numbers is telling us that the depositional texture still has the main control on the distribution of the reservoir quality. And this is a table that shows the production for several wells in the Appleton field. And this confirms that observation. Here we put, for these intervals, we put the interpreted Facies or the positional environment that we have for these intervals. And what we see is that the highest numbers are associated with the shore face and microbial reef. The other numbers, the smaller numbers, are related to the shoal environment, but there's pretty much no producing interval within the lagoon or in the tidal flat or in the subwave phase and the sub-environment. Now, the next task was to move or extrapolate the interpretation coming from the cores into the non-core sections. For that, it proved very useful to use the gamma ray and the porosity, density, and neutron curves to try to identify the depositional phases and also the order in which they were deposited. As I mentioned before, lower part is mostly reefs, tidal subway-based environment, and the upper part is shore in the lagoon behind, in the tidal flat on top. Everything. So with the patterns that you see in these curves, in this stratigraphic order in which we see the sub-environments, it was not that complicated to figure out the positional sub-environments. Always the thrombolite in the showed an increase, obviously, in the density and neutron porosities, and rather low values in the gamma. And in the muddy sections like the lagoon, or the partner here, or the partner over here, you see that the porosity numbers go to the right of the scale. And here we have an example of a well log of a well located off structure and one located on the structure, very next to the crest this is in the vocation. And you can see what I was mentioning, the increasing porosity in the microbial reef and in the shoal facies. This is an interveiling of shoal in tidal flats. I'll show you later on that we have here like high order cycles or our parasequences that are showing this like this smaller variations in sea level. But what is interesting here is that what the section that is on the eastern side of the structure, very close to the crest, has the presence of microbial reefs. Well, this well, located in off-structure location, there's an absence of this microbial reef. You will see now why is that. So this is a well cross section of the vocation field where the previous wells are from. And what you can see here is the distribution of this sub-environment in the Smackover Formation. Here you have the Smackover, this Northlet on the lowestmost part of this section over here to the west. Then you have this short face environment to the west, while you have the big development of microbial buildups to the east. And on top of this, well, in off structure location, the well from the previous slide, you just have the subtidal subway base and on top of this, you start seeing what was interpreted as the shoals here with the higher porosities and low gamma rays. And behind the reefs and these shoals, you have the lagoon. This is muddier section, but with some infections in the well logs. They are telling us that there's some high frequency cycles going on or sequences going on for this area and the Appleton field area. We identify between 14 and 15 these of sequences, telling us that we are very close to level at this point, so we can register any minor changes. Sea level. Here are the location of the core section. This is how it looks like on the seismic. It's more or less the same section. You see the vocation field, and the vocation structure was never completely filled, covered by this Smackover Formation. And here you can see a detail of how the seismic look like on the western and on the eastern side of the structure where you have the reef. So the reefs are located where the paleotopography is more tends to go to the horizontal, and on this eastern side, probably because it was a more isolated and protected side, since this was probably the windward side, and this was the leeward side more protected from the action of winds and currents and things like that. So it was a more quiet and restricted environment over here. You can see here in the seismic how the reef, where we have the reef, you can see this negative wiggle, and it marks the top of the reef. It is absent where you have just the fine-grained subway base. This way was how we map the microbial buildup space. Again, on a higher porosity of the structures compared to the anhydrite here, which is marked by this positive amplitude and also a positive amplitude of the basement below. Here's the three-dimensional interpretation. Here are the paleo highs that were not covered by the Smackover. Here's another small paleo high. Look at where it was covered. The reef developed on all over the structure. Here only on the eastern side of the paleo highs. Now we used the core data to try to populate the whole 3D block. And this is what we get, where we can identify the higher porosity areas that define the microbial reefs in the shoal environment, and the low porosity areas, which define the lagoons behind the reef and in the shoals, and also the tidal flat in the Facies and Hydrate. They're also very low porosity as we move offshore. This is this similar display, but now for the Appleton field area. In this case, the paleo high was completely covered by the Smackover, and you have the development of the microbial reefs on top of the basement surface, where again where the slopes are, and to go to the horizon. Again, you have here the subwave fine-grained facies, subwave-based deposits, and right on top of the structure, the development of the reef. This was covered later, the shoal and tidal and shoal in lagoon facies, and then capped by the tidal flat deposits, and later on the subaqueous. The right button. How it looks like on seismic. We have the strong peak that defines the top of the Smackover, or the top of the Buckner, to be more precise. The top of the Buckner in Hydrate. Then we have this peak that marks the top of the entrance into the buildups, probably also the shoals. And then, as we hit the bottom and the top of the basement again, and here we have just the northern below, big negative reflection. Since we get into 60. This is the three-dimensional interpretation. This is the prismatic over surface in the Appleton field area. So what you see is pretty much homoclinal. Here is just the ramp, but we're in this particular area where you see all these bumps, these are blocks, lifted blocks. Then you have the development of the microbial reefs, which fields defining this. Here you can see this is a seismic line that goes this direction. Here you can see how close is the active limit of the Smackover deposition there. And again, the negatives mark the top of the same thing we did for the Appleton field. So here's the three-dimensional interpretation that's going from one well to the other. And here extrapolated throughout the whole entire area, seismic block. And again, you see the high porosity intervals belong to the microbial reef and the shoals, and the low porosities that correspond to the subwave base, lagoon, the tidal flat, and the saline. Another much the same thing. phase. With this model, this geologic model, let's talk about the deposition and evolution in the area. But before that, I want to use these two graphs to kind of review some basic concepts about the carbonate fabric. What happens is that carbonates, let's say we have basement high or platform being flooded in a transgression. What happens first is that the carbonate production lags behind the increase in sea level, while the organisms kind of settle down and colonize this surface. So at the beginning, carbonate productivity is rather low in what is called the startup phase of the carbonate productivity. Then the carbonate production picks up really fast, and you start to see this aggradational development of carbonates trying to catch up with sea level, just filling all this accommodation that is available for them to grow. This is called the catch-up phase, and here you see the growth curve really is steep. And then, as the transgression comes to an end and you start entering into the high stand, and the seawater rise slows down and gets into a standstill point, then carbonate productivity also slows down, just keeping up with the small increase in sea level rise. And the excess of material then is being either eroded and shed on the flanks of the structure, or it just start to grow in a progradational way outwards. Then with the following sea level fall, the carbonate factory eventually shuts down, and with the following transgression, it just gets. So let's apply these concepts to the position level, first invocation. So as I was mentioning here, at some point, remember this is a marginal area, so probably at the late transgression system strike, we have the flooding of this area, and the position of slightly higher energy, like short phase deposits, on the western side or the windward side of the structure. And here in this more protected, isolated, restricted area, we have the development of microbial reefs. Then we have the sea level still decreasing, the static sea level still decreasing. We have thermal subsidence acting. Remember at the beginning we mentioned about the extensional tectonic present there, so we have subsidence going on, and static sea level rise also happening at the same time. So we have a lot of creation of new accumulation that these deposits are to catch up at this point. So we have here a faster development of the microbial reef in an aggradational manner. Here and here also, it's like the backstepping of the shore. Then, as we kind of reach the highest point of relative sea level, the microbial reefs and the surface deposits here, it's kind of start to slow down and beginning to prograde in this case, just keeping up with sea level rise. And then as we get into the Heistan, late Heistan. Then we have, there's a change probably in the conditions. Most of these blocks are most of them submerged, so there's probably better circulation, ocean circulation here. There's more energy in the environment with the winds and stuff because there are less barriers. And we switch to this shoal and lagoon complex that prograded rapidly outwards. Yeah? Then we have the deposits of the tidal flats. So we have a change in environmental conditions at this point, which probably led to the demise of the microbial reefs, the replacement by these higher energy. This is an example of Spain, and this is one of the outcrops examples that we will see at the end, where you can see something similar. You have these reefs growing up, and at some point, the conditions change, and they're buried by these post-reef graystone and paxtons, very similar to what we see in the area. Similar story happens for the Appleton field. Again, later in the transgression, the marine waters flooded, in this case completely, the basement paleo high. You have the establishment of the microbial colonies on top of the structure and fine sediments on the flank, right? This is the start up phase of the carbonate factory. See that the carbonate kind of lags behind the sea level, but here, with all this available accommodation, it grows up fast. Of this system. Then, as we get into the Heistan, again, growth or carbonate productivity slows down, keeping up with sea level. And at some point, we have here probably higher order cycles, I was mentioning, for the shoal and lagoon complex, and eventually the progradation material probably eroding the micro reefs, and also the higher energy environment with more particles in a seawater supersaturated with particles in carbonate, will end up producing a lot of sedimented prograde and off structure in every direction. After that, we have the deposition of the tidal flats in the salina to Buckner. This evaporates. And then, after burial due to differential compaction, we have in a geometry similar to what we see here in the seismic. Now, just take a look then at some outcrop analogs in Western Europe. So, during the late Jurassic, Tethys Ocean, the western margin of the Tethys Ocean was opening here. During this time, due to this process, we had thermal subsidence. The time of thermal subsidence, the time of eustatic sea level rise, as you can see here in the chart. So we have all the conditions for the establishment of carbon ramp settings, right? So we're going to visit a couple of examples here. In the Iberian Peninsula, which at that time were located at a geographic location similar to where the Smackover buildups were, that is in a carbonate ramp on the northern margin in the western part of the ocean, right? Kind of it's similar. This is the first example. It's, in the eastern part of Spain, on the western side of the Iberian Basin. Here, Dr. Aurel, professor at the University of Zaragoza, took us this area where these microbial-bearing reefs grew at that time in the Upper Jurassic. So as you see, they develop here as these pinnacle, really steep walls, and with heights of up to 60 meters. There are several interesting things here to highlight. First of all, look at the bottom where these structures, these microbial-bearing reefs, because they are not completely thrombolite, where these structures began to nucleate on this hard encrusted cemented surface, similar to a basement surface, hard and stable. And later on, they start to grow laterally, but then the base, the bottom, the nucleation side, is right on top of the hard surface. This is the first thing. Other thing interesting is this external geometries that have this thrombolite. Here in the bottom is mostly thrombolite. And you see again, like the bolts and pillows that I show you in thrombolites in Chile. So this is kind of typical of thrombolites, but it's more like an external. An interesting thing is you see the interreef facies consisting of fine-grained material, like what we see in Smackover. And finally, we saw this what was identified as a maximum flood surface, where the thrombolite becomes more coral than below. Here is more than 45% thrombolite. Here is less than 45% thrombolite. So what we see here, what we can analyze here, is that we have a element of this buildups during the translation due to the higher amount of accommodation. Then as we get into the maximum flowing surface and the high stand, the regressive phase of the cycle, switches more oxygenated type of organisms building the core, the buildups, and later on that get like buried by these post-reef, probably shoals or shore phase deposits. So there's a lot of things going on here that support our interpretation of subsurface in the Gulf of Mexico. These pinnacles were developed in an inner to middle ramp setting, while the other ones in the Smackover, there's one of the differences, where as you saw, very close to the margin of the basin, so really proximal inner ramp environment. The next place we visited was in Portugal, in the Algarve Basin, in the southern part of Portugal. Here, there is a thrombolite bioarm. The term bioarm is because of to describe these domal structures, the one we see here. Here, this is a more thrombolitic than the other one, but it was deposited at 70 meters of water depth in an outer ramp setting. But they were also deposited in hard rock. Here described as a marly limestone, very rich in glauconite, borrowed and encrusted. Very low sediment background and a stable hard ground for them to grow up. These are, as I was mentioning, mostly thrombolites with some sponge and tuifites layers interbedded, but mostly thrombolites. case, and another difference with the previous ones is that what covers the microbial buildup is not a greenstone, is marly limestone, suggesting that this is particular thrombolite buildup was drawn instead of being buried by shallow. Was drawn, was not able to keep up with level rise, and it was down, and it was again here you can see kind of the pillows or the spherical shapes that the buildups have on the outside. So we saw two very different types of buildups in terms of their shape. This one is a bioarm, very similar to what we saw. It's an example of northwest hill. They're about the same thickness, between 70, 60, 90 meters thick. They cover an area of about 2 to 3 square kilometers, or more than that. And so very similar in this case. This would be in the interpretation of these. Also, we saw in some places, not very often, these peaks probably resemble these found in Spain. Here is a dense table that kind of describes or compares the three sites. So all of them are of Upper Jurassic age. They all develop in the northern margin of the Tethys Sea in the carbonate setting. Bioarms in the Gulf of Mexico are very similar, probably somewhat smaller than one in Portugal, but they are comparable in size. And the ones in Spain are different in that way they're formed by. The predominant mineralogical composition is dolomitic for the Smackover buildups, while it's calcareous in the Eurobasin. The biotic composition, mostly microbial for the Smackover in the Portugal example, and heterogeneous between microbial and coral for the eastern Spain example. Recognizable growth forms, pillows, and but this is more like external growth features. And in the Smackover fields, we found layer, chaotic, and dendroidal, all types of growth forms, but internal growth forms, microbial buildup. Now, the prairie facies are igneous and metamorphic rocks in Mexico, or this encrusted wood and pillar greenstone surface in eastern Spain, and biotubated marly limestone in Portugal. All of them hard grounds, very stable hard surface. The interreef facies, in all cases, are fine sediments. The post-reef facies, in the case of Spain and Gulf of Mexico, are colloidal grainstones and oncoidal grainstones. They are showing an increase in water energy, and probably making part of the Heiston system strat, the next regressive phase. And in the case of Portugal, we have dark mols, indicating that it was really again drawn, the microbial buildup. The environmental conditions, hard substrate, low sediment background in all cases, low energy concentrations in general. Wherever you have changes in the oxygen conditions as you move up in the section into the high stem, you switch to another type of deposit. And in terms of sequence stratigraphy, these graph kind of summarize the main idea. For the case of the Smackover, they develop in the late stage of the transgressive systems and get into the lower part of their following regressive track. In the case of the Iberian Basin is something very similar. They develop at some point during the late transgressive cycle and got into the high stand, but then they were covered by this. And in the case of the Algarve Basin, probably because it was in a more distal area, it started to develop early during the transgression. It was not able to reach the turning point and it was drawn before we got into the regressive cycle. This graph shows a summary of all the types of buildups that we saw in Gulf of Mexico and in Europe, and the different water depths that they are interpreted to be developed. Here are the Smackover shallower examples in an inner ramp, middle ramp deposits of the Conecuh Reefs in Spain, and higher water depths, the Thrombolite biome in Portugal. Probably this is an example of like the biome we saw associated with the methane seeps, the Black Sea. So in general, we can see they are not really affected by water. This is not the only variable that don't affect the growth of these, or the development of these thrombolites. They're eurotopic organisms because besides water depth, they are not restricted either by salinity, light penetration, oxygen content, or nutrient supply. They basically can develop where other reef builders can't because of extreme environmental. However, they need some conditions. They need normal marine conditions for this same reason. They need 0 to low background sedimentation for initial growth, and low to moderate sediment background after that. Low to moderate energy, and a hard and stable substrate for initial. Finally, as conclusions, we have identified 7 shallow marine depositional environments in the marginal Smackover. Then we have the Smackover accumulation in the deep active basement ridge plate is defined by a transgressive regressive cycle controlled by different factors, including alloctons such as estuary and thermal subsidence, and local elements, mainly peritopolar carbonate productivity and climatic conditions. The transgressive phase is marked by the accumulation of low energy subtidal sediments of structure, surface and microbial buildups in a retrogradation fashion on spot. The regressive phase is characterized by shallowing upward, higher order cycles, showing the progression of the shore phase shoal environment. The Diagenesis, although very extensive, a lot of diagenetic processes going on in the Smackover, is still not the main control on the location of the main reservoirs, which are mostly the result of the initial depositional texture of the rocks. So in this way, the thrombolites in the shore phase Facies are the best in the area. And field observations in Spain and Portugal validate the model proposed for the Arctic Smackover plate in terms of the positional phases with agents, environmental conditions, and sequence. With that, I think I'm finished and I'm open to questions. Thank you very much.
Juan Carlos, thank you for your presentation. And thanks to all of our 110 participants for joining us today. Starting right now, we will have our 30-minute question session. We have already collected the questions so far, and you can continue to ask them here in case you have more. The presenter will be reviewing them and answering them in the most appropriate order to maintain a good flow. So, thanks. I just sent you an email.
Yeah, I'm just opening the email. Yeah, I can see it. Alexander DeSantis, was it possible to use any seismic attribute to map the reservoir quality in this area? I'm pretty sure it is possible, but it was something that we did not do. And it was mostly because we have an extremely high control with the abundant wells and in very short distances. So we thought that the well control was more than enough to define the extension of the reef. So that's why we didn't use any seismic attribute, but I'm pretty sure in areas with no control we can use it to define the extension in the location. Very nice porosity mapping, but why is of structure? Is it because the microbial buildup wasn't growing up there in phases change? Well, the extension of the, if I understand the question correctly, the extension of the mapping was limited by the extension of the seismic. The seismic invocation was only barely covering the location structure. It's very small. In the bigger one in Appleton, we interpreted the whole thing, and we were able then to see, like for example, the update over deposition, like that. In terms of the micro buildups, they just don't grow like farther away than the in areas that don't have paleohydrates. And this is something that is kind of common to carbonates in general. The reefs, they will develop in highs, probably because they're more protected there from passing sediments and things like that. So what we see here in these fields is that the microbial buildups were strictly restricted to the paleohydrate. More than that, they were restricted to areas where the topography was not very steep surface. Thanks for sharing your work with us. From the 3 models, the porosity values tend to correlate with defined depositional facies, which imply a constraint of ecophysical properties for the facies model. We first create a conceptual model. It was more or less the same order as the presentation had. What I did first was the description of the course. And remember, I had about 2,000 feet covering all the depositional phases. So what I did first was, half of the work was describing this course and describing the thin section. Then from that, we went into the logs, and remember, we didn't have we just have triple compost. It was it, run array or SP, resistivity, and density porosity curve. That was pretty much it, what we had available. So well, they were drilled in the 70s and 80s. The well logs available are advanced, just everything was based on description of the rock, and then trying to extrapolate these interpretations into restricted set of curves. Next question is: Thrombolites bioworm can be related with serpolite bioworms. There's actually there are serpolites in the, example in Portugal. I don't know what this can be, but definitely they can be at this example. Mario, please, thank you for your presentation. How does the energy of waves could affect facies on carbonates, groundwater, setting of the reef, example, aerial reefs, present? There's several questions here. How does energy waves could affect carbonates? In this particular case, the increase in energy resulted, or is the result of changes in the environmental conditions. Mostly, you have more energy, you have more erosion, you have probably also more oxygenation of the waters. So the environmental conditions change, then you have also a lot of particles floating in the agitated waters. Grow as voids. So the resulting carbonate deposition, or what we had previously, when there was no energy or very low levels of energy, low oxygenation, with increased energy, probably as this probably it would probably affect the development of these thrombolites. Now, what we see in thrombolites, when you ask thrombolites could be present, we haven't seen, or that I know, I'm not an expert by any means. I don't understand studying thrombolites all over the world, but in the examples I see, there's always extreme conditions related to it. The ones related to higher, extremely high salinities, like in the case of Shark Bay, the methane in the water, obviously toxic for most organisms. Also a high alkalinity in the, like Sarmiento in Chile, there was one of the, what is the, I showed you with the classification of thrombolites. So yeah, they're developed wherever there are extreme conditions. Why is that? Because otherwise, under regular conditions, they cannot survive. They will be displaced by bigger reef builders like corals and things like that. That's why you will find them mostly in these extreme environments. Now, another question from Henry Galvis. And Carlos, thanks for this very complete presentation. I wonder what was the role of plastic input coming into the buildups, if there was some. Well, to answer the first question, it was very low. The amount of CDC plastic was less, in all cases, was less than 3%. In all the section that I went through, there was more than 200. Why was that? As I explained, it was a very arid climate. Also, there was the material that could be eroded was mostly a crystalline of like some paleozoic basement, so it was hard to erode. But in an arid environment, dry environment, there's no weathering and there's no currents bringing a lot of division of sediment into the basin. So there was one of the reasons that favored the development of the carbonate fabric. This following question is, what was the main factor shutting down the carbonate factory, preventing the growing and well, it's not before the correlation, is basically because of the correlation, because of the changes in the environmental conditions. Again, higher energy, more oxygenated waters, and the accumulation or deposition of huge amount of material that build up or make up the all these bracing barriers. Probably suffocated the shut down the microbial. Next question is, what are the substratum of these different buildups? We talk about that in the summary table. All of the substratums were of different origin, but they share similar conditions. They were hard, stable, and kind of horizontal surfaces. That's the common thing among them. But one was a starting surface, another one was cemented greenstone, and another one was the basement permeability. Alexander Santos, here you seen any relationship between the anhydrite layers of carbonatic reservoirs quality? Thanks for congratulations. Thank you very much. Yeah, what happens as you come close to the anhydrite layers, you gradually start to see an increase in these anhydrite nodules that are protruding the granular and the porosity. So as closer as you get to the bottom of this layer, as Gibson at the beginning, then your porosity substantially reduces. And also, what was in direct contact with the anhydrite layers is the tidal flat deposits, which are fine grained, not with very high porosities, except in the case of the presence of microbial mats. But yeah, in general, as closer as you get to the evaporites, then you will see precipitation of them in between the system of the adjacent rock. And Joseph asks the depositional analog from Spain, highlighted in ordered subsections, from inner ramp to middle ramp. Was this same order succession identified on the well logs and how incorporating the phases? Well, all of the three examples were developed in the same ramp location all the time, vertically. The Smackover was in a very proximal inner ramp. The Spain example was in an inner to middle ramp, and the example in Portugal was in and all the time you're keeping this, right? And so therefore there's no change through time, or like advancing or into proximal locations as we work in these three examples. And was this same order? Wasn't covered. The much was answered to. It's the same. And you just get more shallower and shallower as you get up the Smackover section. But all of the time you are in an inner ramp. There was all the questions that were in the email. I don't know. Do we have time for more?
I just sent you another email with more questions, and we still have 10 minutes more. So
10 minutes more.
Yeah.
Are the Thrombolite pillows volcanic material, or is just a way to group this sedimentation? No, the growing structure of the Thrombolite resembles like a pillow or like a bowl or something like that, but it's not, has nothing to do with volcanic material. We're just borrowing this term from a description of material basalts, pillow lavas, exactly. But no, it's just different. It's just the geometry, this spherical geometry that display the thrombolites on the outside. There's nothing to do. Did you say that the light is not a limiting factor? No. As you see, we had examples, currently examples in the Black Sea where buildups grow at 700 meters of water depth. We saw also the example of Portugal where they grow according to Leinfelder. This microbiome grew at 70 meters of water depth. And then we have the other stream examples where you have the stromatolites in the base that are intertidal environments. So sometimes they are really exposed and they don't have any problem living with that. And also the examples in the Smackover, which are very, very shallow in the inner platform, or the examples in cliff tunnels, where they, remember the picture, they are pretty much on the beach side of the lake. Yeah, thanks for a great talk. Thank you very much. I have a question. Why were the microbial buildups the Appleton field able to grow on top, whereas the Vocation field microbial were restricted to the environments? But the main reason was because in the Vocation, the rest of the structure was never covered by Smackover sediment, so they will never reach was high enough to cover completely the structure. Why was it Appleton present all over the crest of the structure? I don't have the exact answer for that. Probably the conditions there were of much lower energy. I don't know, some variables that I mentioned that are necessary for these buildups were present in Appleton, even at the crest of the structure. While in Vocation, these conditions met only on the leeward or protected side of the structure. The lithologic record is telling us that on the other side there was high energy going on because we had deposition of grainstones and Basin. So they're interpreted commonly as deposited in higher energy environments. You have mentioned that the Smackover is organic reef facies. Organic reef facies were some other facies, marine shells of the formation. They're not the reef facies. They're basically all these mudstones deposited on the deeper sides of the basin, and obviously are obstructed from these. And these, something similar to the first deposition facies that I described, this of wave-based sediments, which were dark and very fine, probably dark, and with a lot of organic material, seams of organic material in there. So they are the ones that are more rich in organic material, and there was the facies that acted as, they were called dense and brown. Rodriguez, I know this guy. Carlos, thanks for your. Is there any potential in Colombian basins? Well, the answer can come in different. The first thing is, from what I have seen, there's nothing similar to a thrombolite buildup here in the Colombian basins, but I don't know. Probably I've been concentrating since I came back to Colombia. I've been concentrating in the offshore and the Lower Magdalena Basin, you know, this kind, everything that is next to the Caribbean area. There I've seen other kind of reservoirs of buildups, not exactly thrombolitic, more related to red algae more than cyanobacterial red algae, red algae and macro forums, but no these type of deposits. Why not? I don't know, if maybe they are there somewhere and we haven't seen them. Wherever you met stream conditions and on top of that, low sediment background and hard surface, they might grow up. I don't see why they wouldn't. But so far, I don't have a record of Thrombolite buildups per se here in Colombia, but it's something that is still a matter of reason, really. But right now we don't know, but I don't see why we wouldn't, as we met these conditions. Jose Vasquez, can you please clarify how you would identify the microbial reefs on some logs? Well, probably with more sophisticated logs, it would be easier to do, but at the time, as I mentioned, we only had basic logs, really 5 logs per well, 5 curves per well. So what we used was, first of all, we know that the big microbial reefs were developed in the lower part of this microbial. Second, they tend to be the most porous facies of all the facies we identify in the. So wherever we had these big intervals with high porosities, where the two density neutron curves kind of shift to the left, we thought that, and in the lower part of this microbial, we were able to corroborate with what we were talking about microbial. Any oil production from the short facies on the western side of the basement, in your example, location field. From the short facies, no, because they were below the oil water contact. That was not the only reason, because it was a good candidate for a hydrocarbon reservoir, but it was down deep in the section. It was always below the oil water contact. Please, can you tell us something about volumes and economic analysis? Unfortunately, no. First of all, it was done like 20 years ago, so I could have. It's really not updated, very old, and I didn't have access to much of the information, especially some data from the Appleton field, and the table that I presented with where I showed that all the productions come from short phase, short phase facies. Mostly, the highest production was where you had not only short facies but also reef facies. They showed production, so I can tell exactly how much was. But we can go back to the table and see what were at least the daily production, not any more than that. Sorry, I can. Did you show core photos? This is the last question of your microbial facies. And were there any evidence of vertical changes in the amount of associated core sponges? No. Well, yeah, there are several photos that I show, and there's no changes in the core, absolutely, or sponges. Well, there are some sponge. Probably what was interpreted as small sponge fragments, but nothing really certain. We have some echinoid spines and things like that, but not really evidence for a good development of any other type of bigger reef. No. I am.
Juan Carlos, excuse me.
Time is over.
Yes, I'm so right.
Well, thank you very much to everybody. If you have more questions, well, my email is available at the Visiting Geoscientist website, so you can send me the questions, and if I can answer them, if I know the answer, I will be happy. So thank you very much. I need to get prepared for this thing. Start all over again.